Okay. All right, so we go to this example 5. Okay, so you have been given a task to design a parallel resonance circuit, which will be a radio receiver that operate at 50.9 kilohertz. Your boss give you a resistor, okay, with a value of 100k, inductor of 20 millihenry, and a variable capacitor. So find a value of capacitor that make the receiver operate at right frequency. Find also the quality factor, bandwidth, and the half power frequency omega 1 and omega 2 of the circuits. Okay, so for the solution, okay, you just write down all the formulas and also all the information given. Okay, so in first place, okay, you have to find the quality factor, right? Okay, so now, okay, so you have the capacitor, okay. Okay, find the value of the capacitor. Okay, find the value of capacitor. Okay, so you have the inductor value. Okay, and then you have the what? Okay, you have the parallel resonance circuit value. So this one is your F node. F node, the frequency resonant, but in hertz. So you have to convert, okay, in radian per second. So you have to multiply with 2 pi. Okay, so you have, so then you get the omega node. Okay, so what, okay, the formula, okay, given you is omega node, right? This is equivalent to 1 over square root of LC. So you just convert into radian per second. So from here you get 100 kilo radian per second. Okay, and then using this formula, okay, so we already know the inductor value. Okay, so you will get the capacitor is equivalent to 5 nanofarad. Okay, so for the quality factor, okay, the second equation is quality factor. Okay, you are using the parallel resonance formula. Okay, so you refer back to the parallel resonance formula. Okay, the quality factor is R divided by omega naught L. Okay, so you just substitute all the values, okay, the respective values. So the quality factor that you will get is 50. Okay, same with the bandwidth. Okay, the bandwidth is omega naught divided by the Q. So you must have the right Q, okay, so that you will get the right value of bandwidth. Okay, so from here, okay, so you get the plug in the formula for the omega naught, okay, divided by the quality factor, and you get the bandwidth is 2 kilo radian per second. Okay, so since the quality factor is larger than is 50, right? So larger than 10, so we can use this formula in order to get the half wave frequency. Okay, the omega 1 is equivalent to, or the lower frequency is equivalent to omega naught minus bandwidth divided by 2. Okay, so the omega naught is 100 kilo. Okay, minus with your bandwidth. Okay, you will get your bandwidth is 2 kilo divided, so 2 kilo divided by 2 is 1000. Okay, so you will get 99 kilo radian per second. Okay, for the omega 2, okay, or the upper frequency, okay, the omega naught plus with your B divided by 2. Okay, so your resonant frequency is 100 kilo, right? Okay, and your bandwidth divided by 2 is 1000. Okay, so you plus these two components, so we get your upper frequency is 101 kilo radian per second. So we go to the next example. Okay, example 6. Okay, so you have a band pass filter as in figure. So this is the band pass configuration. Okay, which has a lower cutoff frequency. Okay, is 400.2 kilo radian per second. Okay, and the upper cutoff frequency, okay, at 400.4 kilo radian per second, and the resistance is 30 kilo ohm. So find the suitable capacitor and inductor values. Okay, by assuming that your quality factor is larger than 10. Okay, so now, okay, you are using this, you have this formula, right? And if you refer back, okay, to the band pass filter, okay, so the configuration of RSC are in series. So we are using the series circuit formula, okay. And then given that the omega 1 for the low frequency is 400.2 kilo radian per second, and omega 2 is 400.4 kilo radian per second, and your R is 30 kilo ohms. If we assume that Q is greater than 10, okay, normally the Q is greater than 10, okay, and then in first place, okay, so you find the bandwidth. The bandwidth is omega 2 minus omega 1, okay, so you deduct, okay, you deduct the omega 2 with omega 1, omega 2 with the omega 1, okay, so you have the bandwidth is 200 radian per second, okay, and then omega naught, okay, we know that omega naught is omega 1 plus omega 2, okay, divided by 2, because the bandwidth, right, the omega naught is in between the omega 1 and omega 2, okay. So you just plus these two, omega 1 and omega 2 divided by 2, so you have the omega naught in between of them, okay, is 400.3 kilo radian per second. And then you can get the quality factor, okay, the quality factor is omega naught divided by B. Okay, and then from here we know that, okay, the Q is greater than 10, even though we are assuming the Q is greater than 10. So now our assumption is correct. Okay, so you get, okay, the Q is 2001. Okay, and then, okay, the question, okay, want you to design the suitable inductor and capacitor for the band pass filter, right? So your L is equivalent to, okay, okay, if you refer to this, okay, is QR divided by omega naught, okay, from the quality factor, okay, so you get the L here, okay, the L, and then you putting all the values inside, okay, the formula, so you the L give you 150 Henry, okay, for the capacitor here, okay, this formula, okay, so you substitute all the values, okay, okay, and then finally your capacitor, the suitable capacitor for this kind of band pass filters is 416 picofarad.